So this Daniell cell, right, it is based on redox reaction. I think we already know that what is redox reaction and all, oxidation as well as reduction. And oxidation means loss of electron and reduction means gain of electron.
Of
So
electrons.
whoever loses electron, right? So if, say for example, if there are two entities, right, this and
Yes,
this,
sir.
and loss of electron, that means now if this will lose electron, so it will lose electron to someone, some other entity, right? Suppose electron is moving from here to here. Now this is suffering or going through loss of electron, so this will be something which will be oxidized, right? But by giving electron to it, say for example, if this is A, this is B, so A is giving electron to B, and by doing that, what happens to B? B is getting reduced. So that's why this A is reducing agent, and just opposite with B, that is B is oxidizing agent. Clear what is reducing agent and what is oxidizing agent?
Yes, sir.
The one which is getting oxidized is actually reducing agent, right? So always from uh, reducing agent to oxidizing agent, there will be transfer of electron. So this picture should be clear always in our head. This is the basic of electrochemistry, right? Okay. Now, if we have a strong reducing agent, correct? So what is a strong reducing agent? Strong reducing agent means who is eager to give electron. So a strong reducing agent can be identified by its attraction for electron. So a strong reducing agent will have weak attraction for electron, and just opposite in case of strong oxidizing agent. It will be strong attraction for electron. Oxidizing agent will oxidize other. That means it itself will get reduced. That means if it is a strong oxidizing agent, its attraction towards or for electron will be more, very high, right? And now based on this, whether there is, I mean, the strength of reducing agent or strength of oxidizing agent, a table is created. That table is called electrochemistry table, and that table is entirely based on, you can say, so instead of doing both, that is reducing power or oxidizing power, we take only one scale because we know that they are connected. So if there is a strong reducing agent, it will be a weak oxidizing agent. So we know that, or it will have weak attraction for electron. So this redox, that's why it is redox, because reduction and oxidation are connected. So the table which is created, the electrochemical series, in that you must have noted that there are, or the data which is noted there is only the reduction. It's actually, it may be also called a reduction table. So it has only standard reduction potential of each electron or for each reaction. So say for example, if you see that table, there will be few entries. For example, say Ag plus. So Ag plus aqueous will take one electron and it will become Ag solid, right? And same way, Cu2 plus in its aqueous solution will take two electron and it becomes Cu solid. Next, say for example, Zn2 plus, the table if you have in front of you in your textbook, you can see that. So this will also take 2 electrons and will become Zn solid. And say for example Mg, so Mg2 plus will again take 2 electrons, and it will become Mg solid. So what is happening here? All of them are getting reduced. So all of them are actually oxidizing agents, right? So in the table, the electrochemical series, which you see, we note only the reduction reaction, because we don't want to confuse. So only the reduction reaction is there. That means, and now it is the series is such that if you go from, or if you come from top to bottom, right? So the top one is actually a strong oxidizing agent, and right, and if you see the bottom one is a strong reducing agent, right? So this is in this, you can say, in this way it is arranged in your table. What does that mean? That means simple, that is, when you come down in this series, right, this process is reduction, but Ag plus will causing oxidization of others. Cu2 plus will causing oxidization of, I mean, in this, if you consider this reaction, if wherever this reaction is happening, this reaction means the other component in that reaction will be undergoing reduction, right? So Ag plus electron, this is a strong oxidizing agent, and this is a weak oxidizing agent as compared to Ag. So Mg2 plus is a weak oxidizing agent as compared to Ag plus. That means if you come down the group, this reaction will become less reactive, right? And so it's this reactivity which is being observed, and the table has been created. Now this table, electrochemical table, is even there before the actual knowledge of standard, or the actual knowledge of the procedure of the calculation of standard electrode potential, just by observing their reactivity, right? So always remember, it is a, if there is something on the top, it will be a strong oxidizing agent, and something in the bottom will be a strong reducing agent, right? So this is what this table means. Now we actually use this to form these cells, which you can see here on the left hand side, that is these cells. So this is your Daniell cell. So what is happening here? Here we have taken two of them. If you see, we have taken Zn and Cu, and in our series also there is Zn and Cu, right? Okay, so there is salt of zinc, that is the zinc solution here. So there is a salt of zinc here, and there is a zinc electrode here. And in the second container, there is copper electrode, and with that, there is a copper salt solution. So basically, it is CuSO4 in the second one and ZnSO4 in the first one, the one on the left, right? Now it is observed that the direction of a voltmeter is connected here, and it is observed that the current flows in this direction, right? So if the current flows in this direction, that means electron must have started traveling in this direction. So this is the direction of current. Current is traveling from right to left, and electron is traveling in the outer circuit from left to right. Right? So that is electron flow, and how do we get to know? By this voltmeter. Actually, by the galvanometer, you will know the direction of the current, and by, if we connect it to voltmeter, we'll actually get the potential of this cell which comes out to be 1.1 volt. So this is EMF of the cell, right? What is EMF of the cell? It is, in this case, the voltmeter gives us that reading. And what is that reading? That reading is 1.1 volt, right? This is what we observe. Now, the overall reactions, if you see in the the electrode reactions, that is at anode and cathode. So how do we know it is anode or cathode? So that we derive from here by observing this direction of current. So direction is current is from copper electrode to zinc electrode. Direction of current. That means electron is flowing from zinc electrode to copper electrode. That means this terminal is generating electrode and this terminal is consuming those electrodes. So the one which is generating electrons, that will be called anode, that is negative terminal. But what should we say, whether that is a you can say whether that is an anode or cathode. So for anode and cathode we have single criteria. What is anode? Anode is that electrode where oxidation happens. Just remember this. And cathode will be opposite of it. So wherever oxidation happens, that is anode. Now come to this. We have two half cells, right? Cu and Zn. Now, as you can see, if you go down, then Zn2 plus, then what is written here? If you go down, the reaction is less reactive. That means you have two reactions, reaction 1 and reaction 2. Which reaction will be less reactive? It is the reaction 2, that is Zn2 plus giving Zn2 plus accepting 2 electron is difficult as compared to copper 2 plus accepting 2 electrons, right? And accepting electron means what? Reduction. That means out of Cu2 plus and Zn2 plus, which one favors reduction? It is the Cu2 plus, right, from this table. So this tells us that this is what must have been happening here. And it is also proved by the direction of current. So that means in this half, electrons must be generated in the first half, that is this, or the cell, half cell on the left. Electrons must be generated. And where electron will be generated? Electron will be generated if there will be oxidation. I hope it is clear that it is negative because here current is in this direction. So direction of current is this. That means electron must be generated here. And electron is generated or released in oxidation, right? And that's why this will be your anode. And because this is anode, the second one has to be cathode, right? So that is how we decide whether the one is anode and cathode. And now we know at anode what will happen. Anode oxidation should happen, cathode reduction should happen. And this table also supports our logic. Table also says that out of copper and zinc, copper will be reduced because it lies above zinc in this table. So that's why, or that's how this cell actually works, right? And so electrons are generated here. Electrons now need, I mean, this half. This is the reaction which happens at anode. So here electrons will be generated, and now they'll search for a passage, or they'll like to escape somewhere. So they travel through this external circuit, right? And they reach the second electrode there. So electrons get accumulated here. Now what will happen? In this solution, there are lots of Cu2 plus ions. Those Cu2 plus ion takes or consumes those electrons and become copper solid or solid copper. And what happens eventually, that these are becoming solid coppers and they get accumulated on this electrode. So this mass of this electrode actually increases with time, and just opposite happens here. Means this will actually get consumed. So the mass, or you can say that this gets eroded. Which one? The zinc electrode. So wherever where this oxidation is happening, in oxidation you can see that solid is converting to iron, so it will actually start losing its weight, right, or mass. So this is how this happens, and the only new thing here is this salt bridge. This actually facilitates the completion of circuit, because if that won't happen, we won't say that there is a flow of current, right? So these two cells has to be connected. So they are already connected by the external wire, but for completion of circuit, that is for flow of ion from one cell to another cell, that is from one half cell to another half cell, there has to be a connection, and this salt bridge actually facilitates that connection or that transfer of charge. Charge in this case is nothing but ions. Through this, electrons are not traveling, right? So that is our Daniell cell, or even the galvanic cell also works on the same phenomena. Working of galvanic cell is also same. So there is a reduction half, there is a oxidation half, and we write cells like this. Now this is another experimental setup where 1 minute. So this is another setup. What we have done here is that galvanic cell or voltaic cell, sorry, the Daniell cell is as it is. We have connected an external cell here, right? So this is the external. This diagram is not clear. Let me use this third one. There it is clear. So this one, the cell which you see here, this is an external cell. The above voltmeter, in the above experiment, the voltmeter reading says that it will be 1.1 volt. Now what we do here, we are actually trying to study this in detail, that's all. So what is being done here? What we do here is, this external cell is there and there is a rheostat connected here, right? This device is called rheostat, which you must have seen in your physics lab. Purpose of this is to provide variable resistance, so that resistance we can increase or decrease. Now what happens due to that? In physics, you must have studied that if there is a cell like this and there is a resistance in the path, then what will happen? Say it is of V volt, then if it is resistance is R, and if there is current I, right, then due to the, at this current, at this, due to this resistance R, there will be a potential drop. So the drop will be equals to V is equals to IR, or simply IR. So the current into resistance will be the drop, right? You can understand it in this way, that cell has to do some work. Cell has to work to do some work in order to travel, in order to force the electrons to travel in the external circuit. So cell provides that energy. To complete, to cell provides the energy to electrons in order to complete the circuit, right? Move from one end of the cell, travel throughout the external circuit, and come back to the cell from the another direction or to the different terminal, right? So that's what is the work of or the duty of the cell. Now obviously it provides energy, and that energy will be consumed by these electrons in order to travel the entire circuit. That is nothing but these resistances. Every conductor has resistance. We may say that it is conductor, but still it has resistance. Resistance means opposition it offers to the flow of current. Why it offers resistance to the flow of current, or why it offers that opposition to the flow of current? Because of random movement of electrons in the conductor itself, right? So this, what does cell do? Cell actually forces them to move in a single direction instead of moving in random directions. That's what the work of cell or battery is. So it actually applies force on the electrons of the conductor and causes their random movement to change to a streamline movement, and that is called current. And in order to do that, it has to do some work, and as it does work, it keeps on losing its energy, right? So that's loss in energy is nothing but the potential drop, and that is given by this IR. That means the drop in potential is directly proportional to R. So that means what? Suppose if there is, this is a 20 volt battery, right? And there this current comes here, and this current flows to this resistance, and it comes here. Sorry, this is the negative, right? Let me make this positive. That is positive, and this part is negative. Suppose this is the cell, so this will be the direction of current. So that means here the potential will be equals to 20 volts, and suppose the current is 2 amperes and the resistance is 3 ohms, then total 6 volt drop will be there. That means what? Once we reach here, the current reaches here. Now here the potential will be 20 minus 6, that is 14 volts. And now if these two ends are connected to some other device, then this device receives 14 volt of input, not 20 volt. So it is connected to a 20 volt battery, but there is already a loss of 6 volts in that resistance, and that's why the voltage which reaches to that resistance in this yellow circuit, which you can see here, the yellow part, that is actually equal to only 14 volts. I hope this is clear now. This is how the rheostat works. The way, or this is what the purpose of adding rheostat in these circuits which you see in the three circuits which you see, or three diagrams which you see below. That is the purpose of that. So there is an external cell which is which will have some external EMF. We don't know it, but it should be more. I mean, say around 5 volts. It should be, and there is a rheostat connected here. And as you can see here in the three diagrams, this length, it keeps on increasing. So what actually it does by increasing the length, we are increasing the resistance. Remember, the resistance is directly proportional to length, inversely proportional to area. So if you increase the length, you increase the resistance. So that's why this diagram is made like that. That means the resistance in the way of cell or resistance connected to this cell is the resistance is maximum here, and this external resistance, this is least here, beautiful line, right? And as I said, suppose external is 20 and resistance, and as resistance increases the drop will also increase, or as resistance decreases the drop will decrease. So here that means the drop from the external is very high, drop from the external is little less than the previous one, and drop from the external voltage is least here in the third case, right? So now what happens due to that, now this cell, the external cell, is actually connected in opposite direction of the current which is being produced here. Current being produced here means current being produced by the Daniell cell. This is our Daniell cell. So the current which is produced here, we know that its direction is this, right? This is the direction of the current of Daniell cell. Okay. So I hope you have already understood those parts. So now let's see what is happening here. The current direction, original current direction will be obviously this due to the Daniell cell, right? But as you can see here, this is the positive of the external cell. So in external circuit, the current flows in this direction. External means due to that external cell, the current's direction will be this. Right now, if two cells are connected, so that means these two cells are actually opposing each other, correct? So now there will be competition between these EMF of these two cells. EMF of these two cells means the voltage or the potential supplied by the external cell and the potential of the cell itself. Now what do we observe? We have a voltmeter here which is connected in between, or maybe even a meter or a galvanometer to show us the direction of the flow of current in this circuit. Now what we observe here is this: when external EMF is less than 1.1 volt, at that time we observe these things. That is, electrons actually flow from, we don't actually know the direction of electron first. We actually know that current is actually flowing from zinc to copper. So the direction of current is actually from zinc to copper. Now, why that happens? Because if you see the above, here voltmeter has given us this reading that it will be 1.1 volt. The EMF of the galvanic cell or the EMF of the Daniell cell is 1.1 volt. So that means if external opposing EMF is less than 1.1 volt, then the galvanic cell's EMF wins because it is 1.1 volt. So suppose external somehow we made change in the rheostat and external EMF is set to 0.9 volts, and the EMF of the cell, of the galvanic cell, our cell, is actually 1.1 volt. So that means it is 0.2 volts greater than the external. So if there is a competition between these two cells, EMF, obviously the Daniell cells, the cell which we have made here, its EMF wins. And that's why the direction of the current will be the original direction of the current, right? And these things are, I mean, how do we observe all these things? So that is also mentioned here, that means the electron, the direction of the current will be from copper to zinc as usual, as we have seen above. So that means electron is flowing from zinc to copper. So not the current. Electron is flowing from zinc to copper. That means at electron oxidation is happening, and because at anode, because zinc is going through oxidation, so that's why it will start getting, or it will get dissolved. So that's what is mentioned here. And we can reverse this process as well. How to reverse this process? Make this external EMF to 1.1 volt, and we observe that the reaction has stopped. There is no flow of current and even electrons, and there is no chemical reaction as well. And then we increase the external EMF. And when we increase the external EMF more than 1.1 volt, then what we observe is that the direction of current is reversed. That means direction of electron flow would also have been reversed. That means now electron will actually flow from here. And if electron is flowing from here, that means now this is our anode, because here, what is happening now? Here, now there is oxidation taking place. And if oxidation is taking place, that means whatever extra copper was getting accumulated here, that will again start dissolving, and new zinc will again start accumulating here, right? So this is actually the way these cells are actually recharged. So if you have inverter at your home, you must have seen this happening, right? There will be a box like this. I mean, inside your inverter, or maybe besides that, there will be a box like this, which is actually your battery, right? There will be at least two connectors will be there, through which you get the supply. So this is connected to your home network, and the same network is used to even recharge this. So what is happening here in these three cases, actually the first and second cases, here your cell is getting discharged. So this is discharging of cell, and this is charging of cell. So if you see external EMF is less, that means there is no external resistance. This happens spontaneously. Right? So there is this, that means even if external EMF is less than 1.1 volt, that means even if it is 0, it will go through discharging, right? So that means without any supply of external energy or external agent, this reaction will happen. And that's what is the spontaneous reaction. Spontaneous reaction means the reactions which does not need any external energy to start or to initiate. That is called a spontaneous reaction. So that means this reaction is a spontaneous reaction. So by naturally it is a reaction which is, the cells are spontaneous, so it will actually act as a source of electrical energy. But if you keep on consuming this, then what will happen? The ions from the Zn sulfate will get consumed, and they will all get the ions from the copper sulfate will get consumed, and they will all get deposited on the copper electrode, right? This is what is happening here. This entire copper ions, ultimately will get accumulated here. Now, once that happens, that means what? Now there is no copper plus ion here. So if there is no copper ion here, so the reaction will stop. That is when we say that the cell is completely discharged. So once these cells are completely discharged, they can be again charged by doing what? By connecting it to a supply of electricity, where we force a current in opposite direction. So here, if you see, the direction of current is this, but in this one, if you see, this is the direction of current, right? So we force an opposite direction current in this. So we made current to flow like this. That means this was our galvanic cell or Daniell cell, right? But this has now become a electrolytic cell where electrolysis is happening, right? The external current, the current is actually due to this external EMF and its direction, and the current will flow according as per that direction. So you can see here the current is flowing in this direction. Now, if current is flowing in this direction, that means electrons are actually coming here. So if electrons are coming here, then Zn will have to take those electrons, right? So the ZnSO4, which is there in the solution, that will get consumed, or that will actually consume the electrons which are coming here, and that's why there will be a reduction here. So now this is reduction, and that's why, because this is reduction, that's why this electrode is now cathode. So this should give us an idea about, basic idea about how these cells work, how the same cell is actually how the recharge, or how the cells are of, even these cells can be even charged. So these are also called chargeable batteries. These batteries which you see in your home appliances, right? Not home appliances, in your inverter. So that is actually rechargeable, and that is actually exactly this cell. Inside, I mean, this is the, you can say, the concept on which those cells are made. Normally, the cells which you see in your inverters, they are called lead accumulator cells. So we'll see if it is in our syllabus. I think it's removed for this time. Otherwise, if we have time, we'll go in detail of this. Otherwise, these are the rechargeable cells, and this is the basis, or this is the working of charging of cell or discharging of cell, how that happens, right? So the spontaneous reaction continues if external EMF is less than the cell EMF. It stops when the external EMF is equal to the cell EMF, and it is reversed. The reaction starts in opposite direction if external EMF is greater than the EMF of the cell. Right? So these two cells, galvanic cells and Daniell cell, their work is to convert chemical energy to electrical energy. So that's all for now. In the next class, we'll discuss mainly the Nernst equation, the quantitative analysis of all this, the calculation part, the numerical parts, we'll discuss in the next class. I hope this is clear, and that's all for today.